In this lesson, we will see how the various concepts we talked about so far come together in providing support for distributed transactions. Specifically, we will look at a system called Spanner developed by and used at Google. We will also touch briefly on a few other design points that are considered in some other solutions to offering support for transactions in distributed systems. You're probably already familiar with what a transaction is from other courses. In short, a transaction is a group of operations that need to be applied together in an indivisible manner. For instance, in this illustration, a transaction corresponds to reading the values of A and B from a database, computing new values by executing the functions f1 and then f2, and then writing out those values back in the database. This has to be done with asset properties: atomicity, consistency, isolation, durability. For instance, in this illustration, two clients interact with the database and it stores two shared objects, A and B. All of these can be running on the same machine, the clients and the database. If the operations are grouped in a transaction, as here, then the transactions have to be executed so that either all of the updates within a transaction are applied to the database or none of them. And also, a transaction is not allowed to execute with inputs that partially see just some of the updates made in another transaction, but not all of them. In this case, if tx1 and tx2 execute concurrently, tx1 can compute f1 and then f2 using the initial values of A and B from the database, and then tx2 is allowed to compute the values of A and B with inputs that correspond to the updates that transaction 1 made, or the other way around. But it is not allowed for, say, transaction 2 to compute f1 with inputs that correspond to the updated value of A based on what tx1 did, but with the old value of B. What that means is that the updates that were made within transaction 1 cannot become partially visible to the rest of the system. Or if transaction 1 crashes, its updates cannot be just partially reflected in the database. Transactions are useful for concurrency control when transactions access shared state, and we have to make sure that they don't access partial updates from one another. This is because we want these transactions to execute atomically and in isolation, so that then we can serialize them in a way that results in consistent output. Transactions are also useful for fault tolerance, where we want to make sure that we don't just save some partial updates of the state reflected by the transaction. Like in our bank account, we don't want to just reflect that maybe we have withdrawn some amount from some account, but not that we have also transferred that amount and updated it in another account. When executing a transaction, we want to make sure that either all of its updates are saved or none of them. What that means is that the outcome of a transaction is either that the transaction is committed, at which point its updates will be permanently visible to others and can safely be used by others, therefore, or that a transaction is aborted, and if it's aborted, any updates that may have been made at that point in the database have to be undone. If the user or the application want to or are able to, then they can try to retry the transaction and execute it again. A distributed transaction is just like a regular transaction, except that it is executed across multiple nodes. The state that needs to get accessed and manipulated resides on multiple nodes. So we still have to ensure the atomicity, isolation, correctness, durability if needed, but we need to do that by reasoning about the operations when performing on multiple nodes. A common solution is to rely on a coordinator or a leader, and this is the node that initiates the transaction and then executes protocols such as two-phase commit or Paxos or Raft, so as to ensure that all of the nodes are in agreement in how the transaction is proceeding. This has to be done across participants of a single distributed transaction and also across multiple distributed transactions, since there may be multiple concurrently ongoing transactions in the system. We'll talk now about a system called Spanner. Companies such as Google, Facebook, they have billions of customers or users all over the world. The way they operate is they rely on an underlying data management layer that allows them to distribute the data across data centers, which are geographically distributed across the world. Spanner is a global data management layer developed and used by Google. It was presented in a paper at OSDI in 2012, but this is not just a research paper. Spanner is used in production at Google to store state for Google's Ads and Google Play business and for other services. It has also been made available as a cloud-based database as a service. It allows applications to rely on familiar SQL queries to interact with the application data, but with the added benefit that this data can then be scaled at global scales. This is something that cannot be achieved by using MySQL cluster as a database. To illustrate how Spanner distributes data, let's look at this example that the Google authors originally used. Let's say that we are considering an application which is like a simple social network that has users with friends, and users make posts which can then be seen by their friends. With Spanner, the data of this application will be stored globally and distributed across different geographic locations. At each location, the data that belongs overall to this data store will be partitioned across thousands of servers. We also use the term that the database is sharded across servers. And also, at each geographic location, the data will also be replicated across multiple sites, and this redundancy is needed for fault tolerance and availability. Spanner consists of a stack of multiple components. This is a figure from the paper that illustrates what the Spanner stack looked like at the time of the publication of the paper. At the bottom of this stack is a layer that ensures durability, provides persistent storage. This is like a distributed file system that makes sure that all the state is ultimately written out to disk and also replicated for providing fault tolerance and greater availability. In this case, it is organized in files using a follow-on on the Google File System. This was presented as another paper at the SOSP conference in 2003. And one thing to highlight about the system is that it is optimized for operations that include reads and appends, because delete operations are rare. Then there is a layer that exports the underlying blocks of files to applications in a specific data model. This is so as to not to have to write applications by explicitly having to think about searching through files, but instead this provides something that is closer to what the application semantics need. At the time of this paper, the system used a version of a key value store, Bigtable, which was also presented at OSDI. This was in 2006. As a side note, in between the Google File System and the Bigtable papers, Google published another famous paper in the SOSP OSDI conference series. This was in 2004. They published the MapReduce paper, which is essentially an equivalent system to what the open source Hadoop MapReduce looks like. Unlike the original key value store system, for the Spanner implementation described here, the original Bigtable tablets, these were the logical groupings of data, were slightly modified. First, they included a timestamp similar to a version number. This was needed so as to be able to think about transaction ordering and how operations become visible externally. The second reason why they needed to modify what Bigtable looked like was to better support operations which don't just access or modify a value entry for a single key or for a range of keys, but instead to support operations which access different types of related data. In that sense, what applications really want is not to have to be rewritten to use some new interface, but they would like to continue using familiar SQL queries on the data. As a result, what they ended up with ultimately was a new system layered on top of Bigtable called Megastore, which essentially exports a view of the distributed store that matches a relational database. Each of these tablet units corresponds to a group of related database table entries based on some set of keys. Each table is replicated, and the replicas are maintained consistent using Paxos. As long as a transaction concerns data in the replicas, Paxos is sufficient. Even if we think about a single replica set, the system has many ongoing transactions, and there may be multiple that need to access and update values in the same replica set. Because of this, we need some way to control concurrency. We would need that even if we didn't work in a geo-distributed environment. Spanner uses locks and a mechanism called two-phase locking. This is similar to two-phase commit, but what's being checked by the lock coordinator is whether all participants can also commit to grant the lock, since only then can we consider that the replica set is locked and can avoid any conflicts. Finally, for transactions that span multiple replica sets, they use distributed transactions with a two-phase commit. To see what we need in terms of transactional support, let's look at some of the examples from the paper. Let's look first what happens when we want to perform a read operation. For instance, we want to read the posts made by all our friends in order to display them on our newsfeed, like in Facebook. If we're trying to get a consistent view of the state of the updates from the friends, we would need to somehow block all of the incoming writes until we capture that consistent view. This is obviously expensive. Instead, we would like to take a logical snapshot view of the state of the system in some sufficiently recent moment. This is like taking a snapshot of the state at the moment that we want to read it, and then taking the contents of the snapshot to create the view of the newsfeed page. Now imagine a Google or Facebook scale system with all its geo-distributed data centers. Clearly, we don't want to block all the writes coming to all of these machines. Remember, each of these locations has multiple data centers and each has thousands of machines. Taking a snapshot would work, but we talked about the distributed snapshot algorithm. It involves many messages, and capturing such a consistent snapshot across all of these machines will be expensive, maybe even more expensive than blocking the transactions and logging. What do? Do we give up on the ability to perform a consistent read? It may be tempting to say that, well, this is just a newsfeed of friends' posts. It's not a big deal if we don't have consistent messages. However, imagine this scenario. You perform two seemingly unrelated operations, one to update your friends list and the other one to update your status post. The two pieces of state could be stored on two different machines, and seemingly there's no causal relationship among them, so they may be reordered. However, you may very much rely upon the fact that the friends list update you perform to remove your boss from the friends list will be applied in the system, and your boss will be removed indeed from the friends list before you make some post announcing that you're looking for a new job. And we could have come up with some examples here that have much worse consequences. In short, consistency matters. In fact, what matters is what we refer to as external consistency, and that the order in which the events are applied in the system must match the order in which the events appeared externally in the real world, based on some global wall clock. In other words, if the system has acknowledged that a transaction 1, has completed at some point of time before transaction 2 started, then it must also guarantee that transaction 2 will see all of the updates that were performed by transaction 1. This property is equivalent to having strict serializability, and we've already talked about the fact that without having a global clock guarantee, we cannot expect to provide strict serializability in a distributed system. Instead, Google uses a concept called TrueTime. TrueTime does not correspond to some absolute real time. Instead, it indicates some uncertainty interval around the real time. For instance, with real time, we have the concept of just reading the real time and finding out what time it is now. With true time, we can perform several operations. We try to find out true time now. This will return an interval, which will give us what the earliest and the latest real time could be at a given point of time. TrueTime also lets us find out two other pieces of information. One is after how much time are we given a guarantee that that particular time that TrueTime indicates has indeed passed. Or it also gives us a way to find out that time t has definitely not arrived in the system yet. By giving us a way to reason about the uncertainty interval of time, TrueTime in a way makes it possible to have a known unknown, which is better than an unknown unknown, right? TrueTime is implemented by using periodic probing of some master clock servers that exist in the data centers. These include both GPS and atomic clocks that exist in the data center that are deployed along at least some of the servers in the data center. And then, depending on the probing period and the probe latency, it is possible to figure out to compute this epsilon value that captures some information about the drift in the clocks, about the uncertainty ultimately that exists between the clock readings in the system. And this epsilon value indicates how off the local clock could be from global time, and therefore it gives us this range of uncertainty. In a sense, when we read the time, it could be up to epsilon time units later than what the actual time is at a particular point of time, or it could indicate a time that's up to epsilon time units earlier than what the current real time is, and that's what this 2 epsilon interval corresponds to. So let's now see how TrueTime would be used by ongoing transactions in the system to determine a timestamp for those transactions. So here's the transaction T, it's happening on one of the nodes, and we want to make sure that we associate a timestamp with this transaction so that just by looking at these timestamps, we can reason exactly about what was the ordering of all the transactions in the system. Now, the first thing we need to do in order to initiate the transaction is we have to acquire the logs that correspond to all of the different objects that are going to be accessed by the transaction. Now, normally, if we were guaranteed that all the clocks in the system were synchronized, we would pick a timestamp. As soon as we acquired the logs, we would pick a timestamp, and that would be the timestamp on the transaction. Because we don't have the guarantee of perfectly synchronous clocks, we use TrueTime to pick a value, and it's going to be this value S, that is guaranteed to be greater than the current reading of the clock at any of the nodes in the system. This gives us a guarantee that if there was a transaction anywhere else in the system that completed before this one, that transaction must have had a timestamp that's smaller than this value S. So we'll be able to order them correctly. Now, we also have to make sure we take care of some issues on the tail end of the transaction. So the transaction is completed when we release the logs. We release the logs, that means that another transaction can start afterwards, and that other transaction will get its own timestamp. So we have to make sure for this transaction T here that the value S that's used for its timestamp is such that it is guaranteed that it's going to be smaller than the readings of any other clock in the system. If we have that guarantee, then we know that the minute we release the logs, if another transaction starts on another node, the timestamp it will end up having will end up being larger than this value S. So it's possible that this transaction was super quick, maybe just update a counter, but we cannot just immediately commit it, immediately complete the operation, acquire the logs, perform the operation, and commit it. We have to wait for a certain amount of time to make sure that we have these properties for the timestamp that the transaction uses. So this is a commit window that each transaction needs to wait out, and it's essentially 2 times the average difference among the clocks in the system. So let's see now what do we do in order to order concurrent write transactions when we use the TrueTime timestamps. First off, we should explain what is the rationale behind this strategy to acquire all the logs up front. This kind of technique is referred to also as pessimistic locking. Now, we are expecting pessimistically that there are going to be lots of conflicts in the system, so might as well get all the locks up front. There is an alternative. We can let the transaction execute, and as we reach a point when the transaction needs to access another object, that's when we trigger the operation to acquire that lock. And that certainly helps in many cases with improving the overall transaction throughput in the system, because if there are other transactions that are happening concurrently and maybe need some pieces of state, but not at the same time as when this transaction is going on, and maybe those are read accesses, it's possible to do that with optimistic locking. The problem is that when we have long transactions and optimistic locking, the likelihood of there being a conflict is much, much greater. So the likelihood that we will have to be rolling back transactions is increased. And in this particular scenario, we're talking about a write transaction. So write transactions have to be replicated. Any update that's performed will have to be replicated to the replicas, so in this case to 3 nodes. So we're basically putting the network latency in the critical path of the transaction. And this is going to create this scenario of having long transactions with high probability of conflicts occurring and rollbacks being necessary. And this is the strategy why in this system there's a deliberate choice made to use pessimistic logging. Now let's see what actually happens in a replica set. So the transaction needs to perform a write. The write needs to be distributed to all the replicas. We need to reach a consensus on whether the write is successfully applied everywhere. And we have to make sure that this gets time-stamped with a unique value. So we pick, as in the previous example, we pick this value S. First, we have to make sure that, again, this value S is correctly chosen with respect to any transactions that may already have completed in the system, so that it's greater than the bounds of that TrueTime interval, than the largest value that any of the TrueTime intervals have. So then the leader of the transaction will start the consensus algorithm, and that's going to take some time. And then we'll achieve the consensus, right? And so at that point, we reach a point where consensus is achieved. We could, at that point, complete the transaction. But again, like in the previous case, we have to wait things out in order to, again, make sure that the clock on all of the machines has advanced in sufficiently to be greater than this value S, so that any transactions that are going to start as soon as we release the logs are going to have timestamps that are greater than this value S. Once the leader releases the logs, it is free to also, actually not just free, it needs to notify the slaves that the logs are released and what was the timestamp that was chosen for this transaction. For transactions that span multiple replica sets, the approach is similar. One node is the transaction coordinator, and it needs to ensure two things. First, it needs to ensure that the transaction will commit only if all of the participants in the transaction perform their share of the updates. For this, Spanner uses two-phase commit. And then internally, each transaction participant has to make sure that the updates that it needs to perform are consistently replicated to its replica set, and this will be done as described before. To do this, the coordinator starts the transaction, and all the participants acquire the logs that they need and compute their TrueTime timestamp S. The transaction starts executing, and each of the participants logs the updates that they are supposed to perform, and this is what's required by the two-phase commit protocol. This is necessary because at this point, it's not known whether the transaction will commit or abort, so we have to do some sort of logging, right? So once we're done with the various updates, we've completed the logging, we are going to notify the transaction coordinator that the prepare phase has essentially completed. And at this point, the transaction coordinator also can find out what is essentially the proposed value for this timestamp based on each of the nodes in the system, and it can compute an overall S value for that transaction. Again, at this point, in principle, we should be ready to complete the transaction, but again, we have to make sure that we wait out the commit period. We have to make sure that externally this transaction will be perceived as ordered before any other transaction that will start later in the system. Again, we have to wait potentially some time before we can release the logs. As before, at this point, the transaction is committed. We notify the participants of the outcome of the transaction and of the value of the TrueTime S, and each of the participants is at this point also free to release the logs. So if we now use this protocol and take a look at the example where we were trying to remove the boss from our friends list, this is what would happen. We would start the transaction, and let's say we would get timestamp 6 at the node that has our friends list. Now another node needs to be involved, or potentially needs to be involved, because we also need to remove ourselves from our boss's friends list, right, from X's friends list. So let's say that node picks 8. This node will log the fact that it needs to perform this remove operation and will respond to the transaction coordinator TC, and it will let it know that its proposed value, the value that it has picked for timestamp, is 8. So at that point, the two-phase commit across these two, the transaction coordinator and the participant, will let us know to determine that the overall timestamp for the transaction will be 8. And so when we issue the risky post, as long as we give it a later timestamp, we're guaranteed that the visibility of that operation will be reflected after this transaction of removing ourselves from the boss's friends list has actually completed. So in this manner, we're guaranteed using this two-phase commit protocol that the two nodes will agree on a timestamp. Timestamp will be 8. And then we're also guaranteed that when the transaction on the participant node, when it completes, it will wait things out. And so transaction 2, the one that is trying to make the risky post, will not even be able to acquire the logs, will not even be able to start until the clock, this true time interval, has advanced sufficiently to reflect that this transaction is going to have a later timestamp. Now, let's take a look at how TrueTime is used to ensure the proper ordering of read transactions in Spanner. We distinguish among two types of read transactions. One type is called read now transactions. So these kinds of read now transactions are the ones that need to return the current value in the system. As a transaction, it's still going to have a leader because it may involve state that's distributed across multiple nodes. And it may also be distributed across multiple replicas, right? We have to deal with making sure that dealing with failures, that the state is really the consistent state of that object. So to order the read transaction relatively to what else is going on in the system, we'll have the leader that determines a safe timestamp. So when is it that it's actually going to return? Whenever it returns, the value that it's going to return, that's the now value in the system, but potentially it will be delayed. This leader, it will determine the safe timestamp. If what's needed is just in a single replica set, then the leader will be the Paxos leader. If what's needed is distributed across multiple replica sets, then we'll do the transaction coordinator that's doing the two-phase commit along with the Paxos replication. By determining the safe timestamp, this is what we mean. This read now transaction is potentially going to be delayed. What that means is that, when we have situations in the system that there are prepared transactions that are not committed, those kinds of transactions are going to delay reads that are being issued against the data store. It's possible that, we don't really need to read the value that's kind of right now. We just need to read a value that it's some specific timestamp in the past. Those kinds of reads can actually be achieved much more easily given that our transactions are timestamped. If our transactions weren't timestamped, what we'd need to do, we'd need to run some distributed cut algorithm in order to figure out what are the dependencies, what is a consistent state, and then actually return that state. But here, because we're guaranteed that the timestamps for the transactions do reflect correctly their external ordering, we can just essentially take a snapshot of the system and then read all the values that we need for, match up their version based on same set of timestamps, and that's going to satisfy these kinds of read operations that want to read at a specific timestamp in the past. So this can be achieved much more easily than if we actually had to run a distributed cut algorithm. So in principle, how do we actually realize this true time? It's not like we have some clock that magically gives us this information about the interval of uncertainty in the system. So a big reason why Spanner was able to achieve this design, it used a combination of GPS and atomic clocks, and it used really fast networking among the nodes in the system. The reports indicate that true time can be achieved with something on the order of a few millisecond uncertainty interval. So what that means is that when we have some operation that's ongoing in the system, in the worst case, this is the amount of time that we would have to delay it. Now, if we don't have that, if we have something like the NTP protocol, that's going to introduce something on the order of 100 milliseconds of uncertainty. Waiting for this amount of time and delaying to respond to a transaction by hundreds of milliseconds can completely render the application useless. Any benefit that we may get from the strict ordering may be irrelevant because nobody's going to use this application. So instead, we recognize that there are many cases where external consistency is not really necessary. So it makes sense to differentiate such cases, and only when the external consistency is indeed needed, then wait out the time or do something more expensive like spend time to synchronize the clocks. One example system is CockroachDB. It's a product built by essentially ex-Googlers that was intended to give the benefits of Spanner for systems that don't have the same kind of capabilities to implement TrueTime. And so it explicitly exposes a flag that makes the question of external consistency or of linearizability of the transactions explicitly visible to the applications. So the application then can choose what are the cases in which achieving this property and paying the necessary delays is really important for the application. One fun fact is that this CockroachDB system derives its name from what was really a design goal for the system. So the system was designed with a goal of survivability. It takes extra care to deal with all sorts of possible failures and, like a cockroach, to survive all of it. Now, when the system doesn't always guarantee that transactions will wait for the previous one to complete, that creates a situation where multiple overlapping transactions operate on the same data, and so they somehow really depend on the ordering of the reads and writes. And they also depend on the outcome of the transactions, whether the transactions are committed or aborted, because this can then lead to all sorts of problems. These situations, when we do allow transactions to concurrently execute, are going to require on some more optimistic mechanism. It's not the pessimistic locking, but instead we'll have to use the optimistic locking, and we will need something that's referred to as optimistic concurrency control. It's optimistic because we allow the operations to execute concurrently, as opposed to expecting them to acquire all the locks up front, as with the way the locking was done in the two-phase locking example that we described in Spanner. But we still need to make sure that the transaction atomicity is preserved, and we have to make sure that isolation requirements, the I from asset, is also maintained. This is what is ultimately going to allow us to ensure that transactions are serializable. Note here, though, that serializable doesn't necessarily mean that they will be serializable in the exact same order as what is externally visible. One popular technique to achieve this is what's called snapshot isolation, and another term for this is also multi-version concurrency control. The reason that we have oftentimes these two different terms for essentially the same concept is because some of these ideas are also coming from different communities, from the database community, distributed database community, from the concurrency and synchronization from the more traditional systems community, and we ended up with same ideas but ultimately different terms. To guarantee correctness, it is necessary to make sure that the order in which the snapshots are used and the order in which they depend upon one another forms a serializable sequence. So if you draw directed lines among the snapshots that a transaction depends on or produces, there shouldn't be a cycle in that graph. If it looks like a cycle will get formed, that's what's an indication of, well, there is a conflict, and then we have to pick a transaction to be aborted and restarted. Spanner is an example of a system that relies on distributed transactions, but distributed transactions are used across all of the big service providers. And another example of a system that makes a different set of design decisions in how it supports distributed state updates is what's used at Amazon in their AWS services with Amazon Aurora. The first obvious difference is that this system follows a primary replica architecture. There is a single primary node that can handle read and write operations, and all of the other nodes are only serving read traffic. That's okay. It makes sense for many real-world large-scale distributed applications, which tend to have way more reads than writes. By keeping the writes localized, the system doesn't really have to perform distributed transactions. It makes very different kind of decision. Part of the reason why the system is designed this way is because it has a goal to guarantee availability of the service even under a large number of failures. The Amazon's AWS servers are organized in many zones. Each zone is independently managed domain, potentially at different locations. And instead of a common replication, Aurora first replicates data to each zone, and then in each zone, it replicates the data to two different locations. By having all these replicas, Aurora makes it possible to guarantee correctness even if an entire zone is lost. And it does so by relying on quorum. It's going to take votes from all of the replicas where data was replicated and will look to see that a majority of the replicas agree. So in a sense, we have to make sure that outside of a single zone, there are enough replicas in order to reach a quorum even if we lose a single zone. Now, one problem is that as a result, there are a total of 6 replicas, and there's a huge amount of what we call I/O amplification. I/O amplification means each time we're trying to perform a write operation, instead there are so many additional write operations that need to actually be performed in the system. By the way, the Aurora paper was presented at a conference called SIGMOD. It's a conference that's really primarily on database systems. So let's look at this I/O amplification. For instance, one way to distribute the ability of the database to serve database requests is just to create a whole bunch of mirror replicas. So this is what is illustrated in this figure. This is a figure from the Aurora SIGMOD paper. We see, however, that in order to ensure that the mirror replica is fully consistent, the primary has to send to the mirror all information about the request that it has served in the form of a log, then all the actual data, then all of the metadata, these are these FRM files, etc. So there's a lot of data that needs to be communicated across these different replica instances. Instead, this is what the I/O transfers in Aurora look like. Aurora uses only log replication. Log, the information about the operations that were performed on the primary, along with some metadata, is the only thing that gets communicated, that gets sent from the primary to the other replicas. This is possible in part because there is already a distributed shared storage among all the replicas. The observation is that if the storage layer in the form of a distributed cache or a distributed persistent store has already been designed and made efficient for data to be accessed in a distributed way, then we don't really need to replicate the same functionality at the level of the distributed operations, at the level of the distributed transactions. The log and the metadata provide sufficient information to execute the replicated operations, to access the necessary data, and to ensure that the operations, read operations in this case, that are visible at each replicas, return consistent data. This data may correspond to slightly stale writes, unless other techniques that, say, use explicit locking are further used in addition with these mechanisms. So in summary, in this lesson, we talked about distributed transactions. Specifically, we discussed what type of system support is needed to make it possible to execute transactions over distributed state in a way that's meaningful and correct. We described several techniques in the context of the Google System Spanner and explained how these are achieved by relying on this concept of TrueTime. And then we also mentioned briefly a few other techniques which are used in building support for distributed transactions and mentioned the systems where they're used, so CockroachDB explicitly and Aurora.